Hi, this is the part 9 of the ArcNLET training video. So in this training video, we're going to talk about ArcNLET simulation without calibration. So here is what I mean calibration. So if you have data, so that could be hydraulic head data, ammonium concentration, nitrate concentration, and you will use those data to calibrate your model. And then you have a model, so this is your ArcNLET model, and then you say, well, I think then you have the model outputs, and then you compare your model outputs with your data, and you're gonna see some mismatch or discrepancy between the data and model simulation. Then you say, well, the problem or the mismatch may be caused by model parameters. So if you adjust model parameters, you may be able to make the match better. So then you go to change your parameter values to improve the match between your model simulation and the observation. This is the idea, basic idea of the model calibration. So we always do a manual calibration. That means we manually adjust the model parameters. There are also software can do automatic calibration, but we do not do it very often. So bottom line is that if you want to do calibration, you have to have data, and especially the data of hydraulic head and nitrogen concentrations. So if you do not have the data, you cannot do a calibration. So you have to run a forward simulation without calibration. So in this part 9 of training video, I'm going to talk about how to prepare ArcNLET's input files and our experience of running ArcNLET without model calibration. So here I have some suggestion for you. So if you do not have calibration data, such as measurements of hydraulic head and nitrogen concentration, we suggest you not running the full ArcNLET, which is ArcNLET v1 plus Vismod, because setting up Vismod require good number of parameter values, and those parameter values always are not quite available. For example, the value of A, we talk about it in the Vismod training video. In this case, you may just run ArcNLET v1, the version 1, because it's easier to set up the model and run the model. And so ArcNLET v1, as we discussed before, is developed to simulate nitrate in groundwater. Here you may consider to simulate for nitrogen, including ammonium and nitrate. This is theoretically not appropriate, but this may give you an approximate nitrogen load estimate rather than a nitrate load estimate. We're going to talk more about this, how to run the ArcNLET v3 later on for our simulation in Eggleston High neighborhood located in the city of Jacksonville. So we have some learning material for you, and at the software website given here, we have the application manual. In this application manual discuss how to prepare DEM data, how to prepare water body file, and also how to prepare hydraulic connectivity in the porosity. We're going to talk about all of this in this training video. And we also have a sensitivity analysis manual. This manual talk about how to determine which parameters are important and why are they important. So actually, we're going to combine the application manual and the sensitivity manual into this training course. And also we have reports available at the project website. We put all our technical report on the website, and it documents all the details what we did for running ArcNLET with and without model calibration. Here we have 3 reports we conducted for the situation without calibration, and then for the other 3 report we talk about how to run calibration, and also we have a paper published about how to run calibration. So here I'm gonna use this report. This is the latest report. We did it to run ArcNLET for nitrogen load in the Kings Bay area in the Citrus County near Tampa. In this simulation, we didn't run calibration. We just set up the model, ArcNLET V1, and then run the model to estimate nitrogen load. So we use nitrogen instead of nitrate just to have an approximate nitrogen load estimate. So this is a report. So again, a lot of figures in this training video are actually from this report, and you can read this report together when you watch this training video. So first, how to prepare DEM data. We always download DEM from a USGS website, but before you download data, you need a clip an area, right? So this is a Kings Bay area with a number of septic tank, and this is from figure 3.1 of our report for the Kings Bay modeling. So you say this is the location of septic tank, but you want to choose the clip area sufficiently larger than the neighborhood for your modeling. Let's say if you have a clip an area small, like this small, just barely cover the septic tanks, then you will have something called a boundary effect, because when you say for you do smoothing, if you do smooth only for this area, you will not have or you will not address the impact of other a DM or other water body, the impact of other DM and other water body on the smooth DM, right? So normally you choose something sufficiently large, cover an area larger than your study site. And then we always go to this website. This is USGS website to download the data, but you may have your own data source from state or county environmental agencies. So if you always have several resolution levels to choose. For example, USGS data have resolution of 10 meter times 10 meter, and some LiDAR data have a finer resolution of 5 feet by 5 feet. The 10 meter by 10 meter is a little bit too coarse to flag the small surface water bodies like creeks, because this is 10 meter. But having a finer resolution like 5 feet by 5 feet may not be necessarily better, because the groundwater table is for sure smoother than land topography. This is the figure you saw before. We have land surface that has a spatial variability, but your groundwater level is smoother, right? So based on our experience, we always choose the resolution of 5 meter by 5 meter or 3 meter by 3 meter. With the computer we have today, I think 3 meter by 3 meter probably the best option we have. And one thing I need to emphasize, after you download DM, do not blindly trust the DM data. It doesn't mean the DM data are wrong. It has been carefully processed and go through QA QC procedure, but this is a DM not for your ArcNLET modeling. For example, in the urban area, it reflects the developed DM, like parking lots and buildings and things like that, and they do not reflect the natural topography of which water table is a subdued replica. Let's look at, this is again Kings Bay example. Let's look at this area. So in this area, there is a parking lot. So we've identified by using the Google Earth satellite picture. So this is a parking lot. We talk about it. So in this DM we downloaded, you can tell the shape. This is the shape of this commercial area, and which is like this, right? So in this the area we have a building, we have parking lot, and so actually the building is pretty high. It's higher than the parking lot, and so in this case you're gonna have like a barrier of with high elevation, so that barrier gonna change your estimated flow path. So you need to do a correction. So what we did here is we correct based on the Google Earth map, and we correct the DEM so that the DEM here would be reflecting the natural topography rather than for the built environment. And so what we always do is, this is our experience, we always first download the DEM data and use it to run the granular flow and the particle tracking modules to generate flow paths. And then we examine the flow paths to see if there are any strange flow paths. So this would require you to have a reasonable understanding of your study site so that you can judge which flow paths look strange. And for those areas with strange flow paths, you need to check whether they are due to wrong DEM, and sometimes they are due to wrong or inappropriate, incorrect water body file. But this is normally what we do. It's probably, if you have a large area, you probably have to spend some effort to study the DEM to see if there anything you need to correct. And we have done some modeling for South Florida. There are some landfill with really high elevation, so you probably want to process that too, so that you can have the DEM that reflect the natural topography. And then there's always options between the regular DEM and the LiDAR DEM. LiDAR DEM is more accurate because it reflects smaller or small surface water body due to its high resolution, due to the high resolution of LiDAR DEM. So for example, this is what we did. This is figure 2-1, 2-2 of the application manual for ArcGIS and Height neighborhood in the city of Jacksonville. In that neighborhood, they built a ditch for surface drainage, and those are ditch information we got from the city. And you see their ditch here. Let's take this ditch as example. In the original DEM we downloaded, it was a long time ago. This research was done about in 2009. It's about 10 years ago. And at that time, the DEM resolution is 10 meter by 10 meter. But from this 10 meter by 10 meter resolution, you cannot tell the ditch, any ditch here. But then we have the LiDAR data later on, and the LiDAR data has a resolution of 5 feet by 5 feet. You can see this LiDAR resolution is definitely better. You can tell immediately the ditch, where the ditches are in this neighborhood. And then the high resolution may cost you high computational cost. Remember, we talk about the numerical simulation is to convert a continuous problem into a discrete problem, and then ArcNLET calculate nitrogen or everything essentially for the raster blocks. So if you have a fine resolution like 5 feet by 5 feet, you're gonna need a long runtime for ArcNLET, and also you need a lot of memory and disk space to save your data. So what we did there is to do a resampling, so that say resampling from the resolution of 5 feet by 5 feet to 3 meter by 3 meter. We didn't use 10 meter, we used 3 meter by 3 meter. Well, you can do 10 meter by 10 meter. That shouldn't be a problem theoretically, just how much detail you want. And you can see 2.1 of the section 2.1 of the application manual for what we did for resampling. That we use a resampling tool built in ArcGIS, and after the resampling, the resolution is not 5 feet by 5 feet anymore, but you can still see the ditch in this area. The next step is prepare water body data. So we normally download water body data from the USGS National Hydrography data set, and this is a link to it. And so here is figure 3-2 in our report for Kings Bay modeling. This is the water body file we downloaded from the USGS website. And it has polygons and polylines for surface water bodies. But again, do not blindly trust the NHD data. And actually, the accuracy of NHD data is not that high. So we sometimes, I would say, for DEM data, they are accurate, but you have to modify it to have the natural topography. but NHD data we often found is not that accurate. Well, take this area as an example. You see here, this is a water body. In this NHD data set, it treated as a water line. That means it's just a polyline. It's just a line, doesn't have any width. So essentially, if it doesn't have any width, ArcNLET will not consider it. And say you have a flow, you're gonna maybe pass this water body. But if you look at your Google Earth satellite data, you see this is not a line, certainly. It has a width. So you have to add a width to this water body. You can do a buffering so that you create a buffer with a height along this line, and then you modify your NHD data within ArcGIS. Then you would have a water body with a width, not a line anymore. And so this is one problem. Another problem is missing water body. Look at this area. From this area, you see there is only one water body. Here is a water body with width. There's a line. But if you look at the DM data we downloaded, this is 3 meter by 3 meter resolution, and you can tell that this part corresponding to this part, but this part is not just a line. Again, it has width, and in this part, you see this is from the DM. This water body is entirely missed in this NHD data. And we check the Google Earth, and we can tell there's indeed a creek here, and so you have to add this water body into your NHD data so that your NHD data can be accurate. So this is the figure we did. This is the original NHD data we downloaded, and then we go through the Google Earth. So Google Earth is good for work, and then we modify the water body. For example, we add water body in this area, and then we convert we change water polyline into polygons. So here, and in several other areas, especially wherever we have a water polyline in NG data, we need to determine whether it's just a very small water body like a line, or you had to buffer it to create a polygon like what we did here. So you can use LiDAR DM or Google Earth satellite picture to identify any problems in HD data, and then you can use a spatial analyst tool, and you click this and then surface, go to contour to generate contours, and then you have to have some data like a depth or elevation of water body, so you can generate contours, and then you can update the water body map using the editor tool of ArcGIS. So those tools are available in ArcGIS. And sometimes we have this problem. You have to build those engineering structure into your water body. So in city of Jacksonville, we have ditches, and in another place, I think it's Orange County, we have those canals. And those canals, you can get those ditch data or canal data from a county or a city utility company. They normally have a good survey, right? So let's say this is DM we downloaded it. There is no information about the ditch polygons, and then you have to post-process the DM using the surveyed ditch data associated with the in the attribute table of this. Again, this is ditch data is in ArcGIS format, and then you determine the elevation of ditches, and then you can modify the original elevation and by considering the ditch elevation. So here this is a processed DM. We just add those ditch information into DM so that the NHD data is updated, and DM data is also updated based on this local information available to us. And so this is sort of what we did. You have to do this manually, so there may be a way to do it automatically, but the modification of the DEM and NHD data are different for a different area. So you have to do it manually, and sometime a field trip may be needed to survey the ditches or canals. If you can have somebody in local, they can probably drive you through, and you have the information you need. And then you can replace the canal um, or ditch components of the flow line with the ditch data that you get from the local government agency or utility company. And so what we did is we used buffer function, and so that you can create a buffer along flow line or polyline. Sometimes we use 6 meter for buffering, but this really depends on the site you're working on. And then for any overlap area, you will delete the overlap area in the DEM or NHD data, but you add your new data into your DEM or NHD data. So here in the NHD data, we have a flow line. This is always a problem, and because polyline doesn't have any width. Polygon normally is okay, an area is okay, and swamp and the marsh, those are polygons, and those are considered as water body because the water flow line or groundwater flow paths gonna terminate at the swamp area, so that if you miss this part, you're gonna have a different load estimates, and you need to add ditch data into your study. Sometimes you see discontinuity of ditch data like here. So when we first look at the ditch data, we say, well, there is a discontinuity, it is reasonable, and then we go to the site and we found out this is a road and it's like a bridge here. So actually things are connected, and so you have to, this is why we say a field survey sometimes is helpful to address any question you may have for the DEM or NHD data. So next, we see how we're going to prepare hydraulic connectivity and the porosity. So we use a Circle database because this database contains survey data at the county level. And this is a website you can download the Circle data, but the Circle data is not ready to use. You have to process the data, and we in the section 2.3 of the application manual, we give a very detailed procedure for processing the soil data, and we give two options. You can process it using ArcGIS, or you can process it using Access. This is a database that Circle store and manage all the soil data. And this procedure are straightforward. If you follow our manual, you should be able to process the Circle data to have hydraulic connectivity and porosity to generate raster files needed for ArcNLET. But this procedure is a little bit tedious, and you have to follow this the procedure we gave in the report. But there may be a way to do it automatically, to do the process automatically, but we have not got a chance to automate the procedure. But one good thing is you can do it for the entire county, and then you save the data for other ArcNLET use. So you model for one neighborhood in the county, and you process Circle data for the entire county. Then if you need run ArcNLET for another area of the county, and you can use this process data for it. So we have some important concept that we feel it's important to talk to you. In the Circle database, data are organized for different levels, and for the Circle contains units and units components and horizons. What we will need in ArcNLET is for soil unit. So you have 1K for each soil unit, but Circle doesn't have, let's say, hydraulic connectivity for unit. This you cannot get it from Circle. That's why you have to process Circle data. Circle will give you at the data at the horizon level. Horizon is the lowest level, so you have a soil unit, which is the blue line, and within each unit you have unit components, and those are represented by the red ellipses, and within each unit you have horizons. The horizons is essentially for layers. You have measured soil properties for each layers. So we need to move the horizon is where your data are. And then you need to move from horizon level to the component level, and then from component level to soil unit level, and then you have a K for each soil unit. Maybe we can look at this picture first. So this is what we did. So you process the Circle database, and then you have a polygon file. Those polygons are for soil units. You see those? You can tell there are many polygons, and those are for water bodies, right? And then and this is for the entire Duval County, where city of Jacksonville is located. So you can process for entire county, and the effort of processing for entire county is the same as the effort for processing, say, for a small neighborhood here. That's why we always suggest you process data for the entire county. And then you have the polygon, and you can convert a polygon into raster. So for each soil unit, you have hydraulic connectivity and the porosity, and then you convert a raster file. So this is actually what you will produce. But how are you gonna process data from the horizon level into unit level? So there are several things to pay attention. So first, while you start from horizon level, and then for each horizon, there are so many attributes or so many soil properties. What we need is hydraulic connectivity, which is labeled as KSATR. R representative, and this is saturated hydraulic connectivity. And then the porosity needed for ArcNLET is labeled as WS. So this is water content, saturated water content. R again representative value. And Circle database has a lower end and upper bound. We just use a representative value. And then for the horizon, I mentioned that it has different layers from near surface to down to groundwater. What we did is we used the data of the lowest depths of the horizon for groundwater modeling. So this is not a perfect way because this is lowest level may not be exactly representing groundwater, but this is the best information we can get. Normally, it's very hard to get hydraulic connectivity for a neighborhood. And then after that, you process the horizon data, and then you aggregate from horizon to component, and then aggregate from component to soil unit, and then you have this figure, and then you convert this polygon file into raster file, and then you can use it to run your ArcNLET. This is for connectivity. When using Circle database in our user menu, we give you an example to assign a constant K over an entire neighborhood. That's actually not always realistic. You can see from this figure, this is again for the King Spade modeling. This is not a big area. But even for this small area, you see the spatial variability. You see here, this is hydraulic connectivity. It could vary from, say, 10 to minus 6 to 21. So it could be several order of magnitude. And this is porosity. It could vary from close to 0 to something like a 44%. So even for this small neighborhood, you always have spatial variability. So we always recommend you to process Circle database to generate heterogeneous hydraulic connectivity and porosity. So how to prepare septic tank data? This is relatively easy. You can have the data from a DOH website. They manage, or they had this website has information of entire septic tank of entire state. Unfortunately, I don't have this website with me. I cannot give a link, but you can contact people in FDOH to get information. And in county utility company, they normally have a location of septic tank. So keep in mind, ArcNLET only need to know location of septic tanks. That's it. As long as you have no location, you're fine for running ArcNLET. And then if you have information of concentration of ammonium or ammonium and nitrate, you can add those in as a column in the attribute table of this septic tank file, right? And so as to the concentration, this which is C0 in ArcNLET, you can use whatever concentration you feel comfortable. And we later on we're going to talk about how to determine this concentration value, C0 value. And then here at this point we already got all the ArcGIS file determined, and the next step is to determine those parameters that you need to run ArcNLET. For example, you need to determine the smoothing factor, you need to determine dispersivity, the denitrification rate, things like that. We're going to talk those one by one. So those parameters are actually very important to your load estimation. So here is an example I prepared for by using this lake shore example as an example. So here I consider 3 sets of parameter. In this set, I consider different values of this is longitudinal dispersivity. This is a horizontal transverse dispersivity, and K is denitrification rate. And those values varies. There's always a range. Say for longitudinal dispersivity, it could range between 0.21 to 21. It's like a 2 order of magnitude. And the K value could range from 0.004 to 2.27. This is from literature, and this is like a 3 order of magnitude. And say for this parameter site, this is a simulated nitrate concentration, and the load is 0.15 pound per day. But if I keep the dispersivity as is, not changed, but I reduce K by half, that means you have less nitrate consumed by bacteria. You see the load is almost doubled, and the concentration become higher. Those things are plotted in the same scale. The concentration become higher because less is consumed by bacteria, so you're going to see a high concentration. So here I keep K as the same for case 3, but I change my alpha. Essentially what I did is I make my longitudinal dispersivity bigger, 10 times bigger, and I make my transverse horizontal dispersivity 10 times smaller, and you can see the plume looks different, and the load looks different too. The load are more than doubled, and the plume become become narrower because I have more dispersed in longitudinal direction, less dispersed in the transverse direction. You see the plume is like this here, but plume may definitely look narrower for this case, right? So this shows the variability of load for different parameter value. Because of this, we always suggest you run your model for different parameter values so that you can have a range that decision maker can use it for making management decisions. So how do we know which parameter is important? We have to run something called a sensitivity analysis. The basic idea is to determine which parameters are important to the nitrogen load estimation. But this is always hard to do, and it's always hard to give you a general guideline because for several reasons. Say first, the parameter importance may change at different sites. It may vary with different hydrogeological conditions and different different spatial distribution of surface water body, things like that. And then even you have different for different sites, you may have different parameters. For example, at one site, you may have 2 hydraulic connectivity value, but at another site, you may have 3 hydraulic conductivity value, or maybe 20 hydraulic connectivity value. So of course, the importance of hydraulic connectivity at one site would be different from the importance of hydraulic connectivity at another site, right? And also, the load estimation also depends on many factors, and one of them is the distance to surface water body. So it's really hard to give you a general guideline which parameter is important, but well, theoretically speaking, so if you want to know which parameter is important to your site, you need to conduct a sensitivity specifically for your site. There are ways to do so, and we document it in the sensitivity manual. You can read through it, but it requires some theoretical background. It may not be easy to implement, although we have done it on our own site. In our own studies, but you may not be able to do it for your studies. So here we only provide some basic information for your reference. So as I mentioned before, the load estimation really depends on many things, such as locations of surface water bodies. What we did here is to conduct a sensitivity analysis to a single concentration plume. We're going to talk about that later. But here, we want you to pay attention. In our sensitivity manual, the results are only for ArcNLET V1 that simulates nitrate concentration only in groundwater only. We have not done a sensitivity analysis for ArcNLET V3. That means if you consider ammonium, things could be different, but we don't know how different it could be. But let's look at our sensitivity study to a single concentration plume. So here is the example. So this is a concentration plume. You have a source. You have a source plane here, and this is a flow direction, and then you have a plume at different time, right? This is this is not time. This is concentration values is higher here and lower here. And so this is just one plume, but this plume, studying this single plume, gonna help us understand which parameter is important to nitrate concentration. And the sensitivity of nitrate concentration may not be same as the sensitivity of nitrate or nitrogen loading, but there is definitely a positive correlation. And the study for concentration gonna help us for load estimation. So this is analytical solution you have seen before. In this analytical solution, it consider velocity. For example, V here, this is the seepage velocity, and the seepage velocity is determined by the smoothing factor, and soil porosity, and the hydraulic connectivity. And also, this analytical solution behind ArcNLET also involve, let's say, K, which denitrification rate, and dispersivity, alpha x and alpha y, which is actually alpha t and alpha hl. This is longitudinal, this is transverse horizontal, and also the source concentration C0. That's a concentration in the source plane here. So this is like a summary of what we did. We use technique, we call it a global sensitivity analysis. I will not explain what global mean, but I can tell you that it consider the variability of those parameters. So this is how we organize data. If you look at this, this is a plume in the X and Y plane. Again, our simulation consider 2D transport in the XY plane. So what we did is we estimate the sensitivity. We have a number of parameters here, right? And this table, this table summarizes the two most important parameter to the nitrate concentration we simulated at different location. And so, for example, this row represent different x coordinates, say between 0 to 50. So this is about x coordinates between 0 and 50 is right here. And then the y-axis is between 0 to 12. That's essentially between 0 and 12. This is up to probably 12 is here. Because the concentration is symmetric along y equal to 0 here, so we didn't consider the bottom half. We just considered the top half for sensitivity study. Essentially, these two sides of y equal to 0 are symmetric. So you can tell, again, for this, we just list two most important parameter, and the K is the denitrification rate, V is groundwater seepage velocity. You can tell those two are always important. And we always also have the dispersion coefficient in the transverse horizontal direction. It's important on the edge of the plume, and near the source plane, and the C0 is important. Of course, the C0 determine how much nitrate or nitrogen gonna enter the system. So why K is always important. So it's all about denitrification. So you can imagine a special case with no denitrification. That means what enters the groundwater can flow out of groundwater to surface water. So in that case, without denitrification, the load estimation would be very easy because all the nitrogen into groundwater will flow into surface water body. In this case, you even do not need a model. You just estimate whatever into the, you do not need a groundwater model, you just need a soil model, and you estimate the load to groundwater, and that'll be exactly the same as the load to surface water body if there is no denitrification. But because of denitrification, actually in part 10 of this training video, we're going to talk about the work we did in two neighborhoods in the city of Jacksonville, and you can see the evidence of denitrification, right? So when we consider denitrification, we use this first order kinetic. So this is change of concentration with time is depends on two things. One is the concentration itself, the other is the denitrification rate. So that means the higher denitrification rate, the faster your K will reduce with time, and the higher the concentration, the faster the decay would be. So this is the first order kinetics, right? And so if you have a high K value, you would have a low concentration, and then you have a smaller load because nitrate is consumed by bacteria, right? So, and if you have a high concentration, it's a little bit more complicated. So you may have more load, you may have less load, depends on the transport process, right? So we need and the concentration itself, it depends on a lot of things. So actually that's why the sensitivity study is not very straightforward, especially except for some special case. Like for K, it would be pretty straightforward. So, and this is a sensitivity. We call this a local sensitivity, and this is different from global. We use local sensitivity simply for illustration. So what does it mean, local sensitivity? Say here, we want to see the importance of the source plane concentration to the simulated concentration at location x, y, right? And then we take x, y. We say x, we're gonna simulate the concentration at x equal to 30, and then the width we take is at 6, but we show the concentration at 2y value, y equal to 2.5 and y equal to 6. What that mean? So let's go back to this plume. So x equal to I said 30, right? Yeah, x equal to 30. That means I'm simulating my nitrate concentration at x equal to 30. And so I have many y values here, right? Then I would take y value at the concentration value at two y location. One is y equal to 2.5, is near the center of the plume. The other is 6 meter, which is far away from the center of the plume. Right? So that's why we say y equal to 2.5 and y equal to 6. Right? That's essentially x equal to 30, y equal to 2.5, y equal to 6, and that's the concentration we're using. So this is the location, but what do we mean local sensitivity? That means, so here we want to see importance of C0, right? Then we have many other parameters. We're going to fix other parameters. We say velocity fixed at 0.2, decay coefficients or the natural friction rate is fixed at 0.008. We fix alpha, x, alpha, y, and C0, and then we change C0. We change C0 between 25 and 80. So 25 and 80. You can see if we have a higher C0 value, we're gonna have a high concentration at the point we picked, right? So just linear a change. That's very straightforward because the concentration is indeed a linear function of C0. Once you change C0, you have a linear change of your C. So this is how important our C0 to the C simulation. And then this is for the decay. And the decay, you can tell, again, we choose x equal to 30, and then y are 2.5 meter and 6 meter. You can see that if you change your k, you change your k from the value of really small, probably 0.008 to say 0.11, right? So you can tell that if you increase the k, your concentration at the 2 points will drop sharply, and then if k is too big, you will have 0 concentration at this location, x equal to 30. That means your all nitrate are consumed before for x less than 30, right? So that makes sense because there's an inverse relation. So the K is always very important to your simulated nitrate concentration. It's also very important to the simulated load. If your K is extremely big and then your job is done, you say there's 0 load to surface water body, but it's always not the case. And this is for excuse me, this is for groundwater velocity, and you can tell that if you have a high value for this, again, this is for this point. If you have a high value of your velocity and this concentration would be higher, this makes sense in that if and this is near the source, this is far away from the source. This makes sense because you have a high velocity and you have the nitrate move fast from the source plane to the 2 points we consider here, right? That make physical sense. And then this is excuse me, this is for dispersivity. And again, if you have a high dispersivity, that means things disperse, you have more dispersivity, and like here, and then your concentration will increase too. And this is like look like pretty much a linear relation between concentration and the longitudinal dispersivity. And then for a transverse dispersivity, things are a little bit crazy. And you see here, for the location near the center of the plume, and that's what I mean near the center of plume. So here you have this source plane, and then this is the center plume, right? And so you have a location near the center plume and far away from the center plume, right? So you can tell that so if you increase your transverse dispersivity, and then near the center plume, the concentration actually going to decrease. But far away from the center plume, your concentration actually going to increase. This makes sense because it's dispersion, right? So you think about the mass. A mass can either be here or there. So if you increase your transverse dispersion, and the concentration gonna spread out, and that's why your plume far away from the center gonna increase, and then the concentration near the center gonna decrease because things all spread out and away from the center of the plume, right? So we did this and to tell when it's where it's important. So this essentially say it's be important at some location will be so the concentration gonna increase with um, transverse horizontal dispersivity, or it's gonna decrease, right? Where is the threshold line? The threshold line is calculated by this equation, right? But you don't need to worry about too much detail about this value. And so this is sort of conclusions we made for the sensitivity analysis. So if you increase the velocity and longitudinal dispersivity and the source plane, and your simulated concentration will increase. And this makes perfect sense because, say, velocity is higher, everything move faster. Of course, the concentration move faster from the source plane. Of course, the concentration far away from or away from the source plane gonna increase, right? So um, and if you increase your first order decay coefficient, your concentration gonna decrease because increasing the decay coefficients means bacteria eating more nitrate. You're gonna have less nitrate concentration, right? And increasing the transverse dispersivity, so if your location Y is less than half of the source plane, you're gonna have a decreased simulated concentration. If it's that means things are gonna spread out. So for the location near the center line, the concentration will decrease if you increase your transverse dispersivity, right? But for the location far away from the source center of line, increase your transverse dispersivity, you're going to have increased simulated concentration because things spread out more to the edge of the plume, right? So we're here to talk about let's go back to the equation. So we talk about the importance of those parameters v and k alpha x alpha y along the flow path, along the flow direction and transverse to the flow direction and the source plate concentration. But what determines v, right? So v is determined by three things: smoothing factor, soil porosity, and hydraulic connectivity. So that's why we have this slide here, right? So you look at the V. So essentially V determined by several things: K, hydraulic connectivity; theta, porosity; and the Z is actually determined by the smoothing factor, right? But one thing I want to keep in mind: a faster flow always result a larger load. That because a faster flow means less time for denitrification. If there's less denitrification, you'll be more load. So if you want simulate a larger load, you're gonna have a faster flow. And of course, this depends on other things like, say, distance to surface water body. That's another factor. We're actually going to talk about this in another training video when we talk about our numerical simulation for the Port-Salusi area. But let's look at this, the factor that affect the seepage velocity. One is smoothing factor. And you can understand this from a conceptual level. So if you use a larger smoothing factor, and then your smooth DM will be pretty flat. So if you have a infinite number of smoothing factor, then everything will flat out because you're smoothing things, right? And then if your smooth DM is flatter, that means your head gradient right here would be smaller. That means your velocity will be smaller. So if your velocity is smaller, and there's more time for denitrification, then you will have a smaller load, right? So that essentially means the larger the smoothing factor, the smaller the load, because you can imagine it's gonna take forever for your nitrate to travel from septic tank into your surface water, and then there will be definitely very small load, right? So hydraulic connectivity, that's pretty straightforward. You have a high hydraulic connectivity, then you would have a high velocity. And then for porosity, and if you have a high porosity value, you have a smaller load. That's pretty straightforward thing. And then question is, how are you going to determine smoothing factor? So the best way to determine smoothing factor is to have a calibration data, which means measured hydraulic head. And then you can compare measured hydraulic head with the smooth DEM, and then to determine what's the best factor. We're going to talk about this in our Drillington Creek modeling example. So based on the example or cases we run for the city of Jacksonville, we always use a value of 50 or 60, and actually they probably do not make much difference. 60 is what you have seen in the Lakeshore example, but 60 is what we use for Kings Bay. But sometimes we use something really big. For a Lake Roberts modeling, which is located in Orange County, we need to use a smoothing factor as large as 400 in order to measure the groundwater velocity in our simulation, right? Again, we're going to talk about how to determine smoothing factor during model calibration in another training video. And then how are you going to determine C0 value, right? So, oh, by the way, so here's the smoothing factor. And for hydraulic connectivity and the porosity, I think you can just download the data and process data from Circle database and use them as is, because it's really, if you don't have calibration data, it's really, you don't know how to adjust it. But if you have calibration data, you can adjust them. We're going to talk about that later on. And then how you're going to determine C0 value, right? Again, you have to count on literature to determine C0 value. In a review article by McRae, it says it's range between 0 and 80 milligram, and actually this should be 25, but maximum is 80. So we use 40 as a nitrate concentration in the Lakeshore example. But if you want to use ArcNLET V1 to simulate nitrogen rather than nitrate, and you may use a larger value to represent nitrogen than nitrate. So in the Kings Bay modeling, we use 57.7 because that's the value of total nitrogen concentration reported in the report by Hazen and Sawyer. Then how to determine mean, right? We have, remember in the I think it's training video part 4 or part, I couldn't remember exact part number. There are two ways to determine mean. You can just give a mean value, and then the software ArcNLET is gonna calculate z value, or you can give a z value, and then the software is gonna calculate mean value. So it's always easier to justify using mean rather than using z, because z, as I explained to you, is pretty much a fudgy factor, but mean you can estimate it based on literature data. So we gave an example before. Here we want to mention it again. So this is how we estimate mean. So we have the nitrogen release per person per day, and multiply to the number of people per household, and then multiply by 0.7. That's the amount of nitrogen not lost in septic tank, right? So you got those data. So this is 4.61 kilogram per person per day per year, and you convert it to per day. And then you have a number of people. Say for the Kings Bay, it's where is it? Yeah, 2.29 person per household for Citrus County, where the Kings Bay area is located. So you can do that to get mean, and you can use it in ArcNLET, and ArcNLET gonna calculate Z automatically. Then how are you gonna determine K, which is the denitrification rate? So this K is definitely subject to substantial uncertainty. In the paper of McRae, it gave a range of this, and in this paper, it gives you a range of this. So again, you see a very big difference between this range and this range, right? And then in our report, we use this range for Monte Carlo simulation. So you have to make your own judgment which one to use. So for King's Bay modeling, we use a value of 0.001, which fall into actually this range, smaller than the minimum value given by McRae. And the reason is that we did a calibration for Port St. Lucie and Martin County. We got a value of 0.0011, and we consider the two sites, the Kings Bay area and the Port St. Lucie area. We found out there's some similarity, and then we use the similar value here. But what's similarity? So in a paper by Demon Anderson, he has a nice figure to show that the nitrification rate is positively correlated with the particulate organic carbon. And so that means essentially you can use organic carbon as an indicator for the amount of denitrification, because bacteria need organic carbon as the electron donor. We compare the POC, or organic carbon or organic matter, for the two sites, for Port St. Lucie and for Kings Bay. Here is the results. So again, this is from soil Circle database, and this is soil organic matter content for Port St. Lucie, and this is soil organic matter content at Kings Bay, and everything, the legends are the same. The color represents the same range of the soil organic matter. And also we did a statistics. This is a histogram for for values of organic matter. So this is for Port St. Lucie, and this is for Kings Bay. You see, they're pretty much similar in the sense that most of the organic matter, soil organic content, are in the range of 0 to 5%, right? So that means the organic content for the two sites are similar, and then we draw a conclusion that the denitrification rate would be similar for the two sites. That's why we get this value from calibration for Port St. Lucie. Then we use a similar value for Kings Bay. Right? And then how are you going to determine dispersivity? Again, you have to count on literature if you have no calibration data. And in a report by Hal Davis for the Naval Air Station, he used a value of 2.134 for longitudinal dispersivity, and this value for transverse dispersivity. And this is another paper for Hernando County, which is south to the Citrus County. He used this value. And so in our simulation, we use the value of in our another model. This is our own model. We also did the calibration for Marion County. So we use 10 meter and 1 meter, right? So based on this, we consider different values to use. So this is always our suggestion. So in the case that you do not have data, you better run your model for different cases, and each case has different parameter values. So here in, for example, we believe our own personal belief that smoothing factor would be 60, so we didn't change it between cases. And so this is also the case for M in and for C0. But for dispersivity, we consider 10.1 and these two values, right? So those two values, this is from our calibration, this is from literature. And then for K, we consider 0.001 from our on calibration. We also consider this value, which is bigger than this value. And this is just example. And when you run ArcNLET for your case, you may pick the numbers that you feel comfortable and run ArcNLET for different cases with different combination of parameters. Then you have a range of load estimate that can be useful for your environmental management. So after you run the different cases, or for each case, what you need to report. Again, this is our practice. We always report the load, because this is the most important thing, right? ArcNLET simulate the load for actually milligram per day, you can convert into kilogram per day, and but you need to convert into pound per year, of course, for your management. And then you need this is what we do. You don't need to follow what we do, and we report the load per septic tank. This is total number. You divide it by the number of septic tank, and then we report reduction ratio. The reduction ratio means you have M in, right? The mass into groundwater, and then you have amount of denitrification, and this is reported in the output of ArcNLET after you run the load estimation module, and then you calculate the difference between M in and M denitrification divided by M in. So that's how much nitrogen is gone. So these two values, we report them because we can compare our estimated values with literature. For example, actually many report a reduction ratio about 70% or 50%. And so once we have our own simulation, we can compare with literature, so we can have some confidence about our simulation results. And for each case, this is what we include in report. You need to include a simulated nitrogen plume. That's like here. This is visual results. People can see it. People can comment. People can make suggestions. And also you need to simulate, and also you need to report the water bodies that receive the largest amount of nitrogen loading, right? So this is the FID of water body, and those are load in different units, and this inflow rate, reduction ratio, number of contributing septic tank, and number of load per septic tank. You divide, so this is gram per day, right? So you need to divide this, convert it into gram per day, divided by the contributing septic tank. This will be load per septic tank, right? So this may be helpful to identify the hotspots of nitrogen loading. Let's see, this is the 34. Let me see if we can easily find. Yeah, so this is 34. This is FID, right? So this is 81, but 34, you can tell this is for the largest part of this Kings Bay area. Of course, this 34 will have the largest number of load, and those are canals, and you have also septic tank near to it, and those gonna contribute septic tank to the nitrogen from septic tank. Is actually, this is 105. This is the second largest water body receiving nitrogen load, and you see here this 105, and of course because it's so close, the septic tanks are so close to the canal, that's why the loading is so high here. That's pretty much it. So as a summary, this training video explains how we're gonna run ArcNLET for a situation without calibration. That means you have no data. You have no data of hydraulic head, no data of nitrogen concentration. You just want to run the model and to estimate the load, right? We suggest you to run ArcNLET V1, not to run Vismod, because Vismod requires so many parameters that you may not have. And then we explain how to determine those parameters, how to prepare the raster files based on the public available information. So you can tell that here we do not have any data, but we can get the job done. We can still have the load estimation. Whether it's the real value or not, we don't know, but at least we have something to work with. So all the data are from the public domain, the DEM, the soil data, the NHD data, the septic tank data, and so on and so forth. And in addition to those raster files or ArcGIS file, we also need parameter values to run the model, like smoothing factor. So we talk in this video how to determine those parameter values. Again, most of them are based on literature and our experience of calibration. So I hope this video will be helpful to you to run ArcNLET. And in the next video, we're going to talk about what we did to calibrate ArcNLET for estimating nitrogen load. So that will be part 10. I will see you in part 10 of this training video series.